Welcome to the University of Pittsburgh's Health and Explainable AI podcast. I'm your host, Jordan Gospore, a health and science reporter. Join me as we cover advancements being made in health informatics and explainable AI for students, researchers, and healthcare practitioners interested in applications of artificial intelligence and machine learning. This podcast is produced by the University of Pittsburgh's Health and Explainable AI Research Laboratory at the University of Pittsburgh School of Health and Rehabilitation Sciences Department of Health Information Management. Headed by Ahmad Tafti, Pitt's HexAI Lab cultivates extramural collaborations with academic institutions both nationally and internationally through its research, educational contributions, and this podcast series.
Hello, and welcome back to the Pitt HexAI podcast. I'm Jamie Gramz, your host for today's session with Dr. Xenophon Papademetris, Professor of Biomedical Informatics and Data Science and Radiology and Biomedical Imaging at Yale School of Medicine. Dr. Papademetris directs the Yale Certificate Program in Medical Software and Medical AI and was also the lead author of the new textbook, Introduction to Medical Software, Foundations for Digital Health Devices and Diagnostics. Hi, Dr. Papademetris. Welcome to the Pitt HexAI podcast, and thank you for joining us.
Yeah, thanks for inviting me.
Well, we're really excited to have you here, and especially given your expertise and your focus on education around AI and software as a medical device. Can you just start things off by telling our listeners a little about your journey and how you became interested in medical image analysis and AI in healthcare?
Yeah, so I started a PhD at Yale 30 years ago, give or take. And I was interested into imaging and problems like that. And the two big imaging groups here were like computer vision and medical image analysis. So I took one look at computer vision and thought to myself, and this was a consensus at the time, so I wasn't uniquely wrong about this. Computer vision is going nowhere. Maybe on the Mars rover, but there are no real applications. Cameras are hard to find. Fast forward now where everybody has a phone in their pocket and computer vision is this thriving, exploding field. What did we know? And I thought medical imaging, well, there's a chance I might do some good there and maybe some applications. So I ended up working medical image analysis. I stayed on here, got a faculty appointment. And so I did some work in medical image analysis. So it's like defined broadly as extracting quantitative information from images. How big is something? How did it change? Where is it? Things like that. And then, as part of that work, I got into software development. I mean, I've been programming for a long time before that, but in order for these algorithms to be useful, to be put into hands of our research collaborators, we had to package them into code they could use, and I got involved in software. And that's how life started and continued for a while. And then at some point, I was asked to teach this class in medical software at the undergraduate program here at Yale. And, at that point, it sort of forced me to formalize some of my thinking in medical software. And then everything else, the Coursera class, the textbook, and whatever else we talk about, sort of derived from what I learned from that class. And, the old joke in academia is that you don't know anything until you teach it. It's actually true. It forced me to learn things that I thought I knew, but until you have to teach it, you don't really know it. So that's how the story started, I guess. And so, 30 years later, I'm still at Yale.
Well, that's great. And you've definitely made a huge impact through your focus on education, be it through the medical software design class you teach at Yale and the medical software and AI certificate program. Can you share some detail on the concepts you cover as part of these programs and why they're important?
Yeah, so what happened was that when we started teaching the Yale class, I really wanted the students to sort of get the entire picture of what a medical software tool is, right? So, and this lies at the intersection of, everything from the clinical application to the math that goes behind the algorithms, the software engineering that helps package those algorithms into a tool, quality processes, regulatory, business, all of that stuff. All of those things come together as an area. And if you don't understand any piece of this, your chances of succeeding are low, right? The perfect looking piece of software that's mismatched with the clinical application isn't going to work. I have colleagues from the School of Management who came and helped out on the business side, but ultimately the greatest tool, if nobody's willing to pay for it, that doesn't help you. So you have to figure out who actually is the interested person who's going to pay? Who are the real users, not just the people who are going to touch it, but the rest of the stakeholders? If you have the greatest tool, but you can't make it through the FDA, again, that's not going to be very useful in a healthcare setting. So that's a little bit of what we try to do there. It's sort of cover the broad spectrum. Now, when we started in 2016, it was a lot of software and a little bit of AI. If you look at the textbook, there's a chapter on machine learning, but, a light touch on it. By the time now, 3-4 years later, we look at the certificate program, and it's basically 50-50 software/AI. And, the two go together, and we'll talk about it later, but AI tools are really software enriched in some ways with some AI algorithms. So you need to understand both sides. And there's a big cultural divide in the field between, software engineers and, say, data scientists, and getting them to talk and work together. But that's the big picture of those things, of what we cover. And so for the undergraduate class, we cover some of the basics, and then we walk them through a design exercise. So we walk through requirements, specifications, design, risk management, testing, validation, all of those things. And we cover some of that in the same way in the online programs, although unfortunately there we can't have people try to do a prototype to practice this thing. So that's the story of those things.
It sounds like you cover some of the core concepts of software as a medical device and the approaches that companies that develop medical devices have to go through when they create software that's used in the healthcare realm.
Mm-hmm. Yeah, I think that was part of it, right? I had talked to colleagues in industry and, learn what their complaints were about the new students they were hiring. And I thought, well, can we do something in this space to help ease that transition in some ways?
Well, it's a great program, the coursework you're doing at Yale, but you also published a great class on Coursera a little while ago called Introduction to Medical Software that now has more than 26,000 students enrolled. Can you tell us about this Coursera class and the types of individuals that might benefit from taking it?
Right. So the number is accurate, although with all online courses, probably divide that by 2 to get to the actual number of people who pay any attention. It's still a good number, though. We graduate more people every month from the Coursera class than have ever taken the Yale class in person. And this is now year 9 of the Yale class next semester. So that tells you something about the scale. So the Coursera class came about during COVID. We were all teaching over Zoom remote, and I had pre-recorded a lot of my videos, my lectures for the undergraduate class. And I thought, well, there has to be some way to make this available that might be interesting to some people. And then I talked to people at Yale and said, well, we have this Coursera mechanism. So we recorded this class. It's about 12 weeks long. I did about 85% of it. I had colleagues from the School of Management saying, people help with the textbook, come and talk about the business side. And then I have some other colleagues to introduce some clinical issues and, cover small segments. And there we start from, what is medical software, work our way through regulatory quality risk, the same. And then we go through the software lifecycle, talk about AI, again, a little bit at the end. And then we finish with, the hour and a bit of lectures that my business colleagues teach on the business side, who are the patients, who are the users. The challenge I have learned, and this is, once you do this work, you pick up knowledge, is that for medical products, who uses, who benefits, who pays are 3 different people. And like when you buy a cell phone and you pay, you benefit, you use, essentially. So those are the additional complexities as we think about these products. But that's the story of the Coursera class. When we launched it, we were looking for maybe 3 different types of people, maybe 4. One was computer science students who want to go in the medical device industry, and they wanted to learn some of the terminology and maybe understand why we do things the way we do in the medical device industry. Even, the details, of course, will be taught by the companies, but just the concepts, quality system, risk, design documents, design controls, all of those things. We also had in mind, regulatory quality professionals trained, understanding the legal quality side, but not knowing anything about software, and trying to give them an introduction of what we worry about when we do software engineering. Maybe a third type of person would have been entrepreneurs, startup founders, just to know who they need to talk to as they think about launching a digital health product or a medical software product or something. And then, aspirationally, I was thinking about people who manage funding mechanism at the government level, sort of more senior leadership, just to give them a very high-level education. We've had students from, every continent, every country, every major company, people at the FDA. At least one person at the FDA has talked to me that they have taken the course. And, it's kind of fun. I go to a conference and somebody walked up to me and said, "Oh, I took your class." I said, "Okay, you put up with me." It's kind of fun. So we've heard from people from, every country you can imagine, a kid in South Sudan who I never thought that they had the time in the middle of the civil war to take online courses, but they did. It was kind of a nice thing to hear about. So it's been nice. It's been fun. I try to go on LinkedIn, and when people post the certificates, I try to like them. So every few weeks I search for it. It's always fun to see, another country that I hadn't heard from before. So the majority of students in these programs, at least for us, are US and India. Those are the big two. But then, other countries may get into the top 10. About 10% of enrolled students are in Africa, which gives me some particular pleasure because those are students that don't often have the opportunity to take courses like that in their own schools. So it's a way for us to reach out, help them develop what they need to develop too.
Well, it's great. It's amazing the reach and the impact you've had through the Coursera class. And in addition to your focus on education and publishing textbook, grading the class, you're also big in the research space. And one recent publication that you focused on, highlighted explainability being a big topic for you. And you participated in a really interesting multi-research collaboration with Yale, Carnegie Mellon, and Dartmouth, publishing a position paper on the topic of lessons from clinical communications for explainable AI. And one of the key points in that paper was that while there's still significant research in the development of explainability techniques for AI, there's a question that remains as to who needs that explanation and what an explanation consists of and how to communicate this to a lay user who lacks direct expertise in this area. Can you speak a little to the explainability and clinical communications aspects that were discussed in the paper and share some of the key insights?
Yeah, so that was part of a collaborative project. It's an NSF-funded work under the Designing Accountable Software Systems initiative. And it was joined between Yale and Carnegie Mellon. One of the Yale people moved to Dartmouth in the middle of the project, so that's how Dartmouth came into it. So the collaboration between sociology, medicine, someone like me who's, medical software, medical image analysis person, and colleagues at Carnegie Mellon who specialized in software engineering with AI, Christian Kastner, who actually is writing a book on AI and software engineering that should be out soon. So what we looked at was explainability is one of the key issues, right? We talk about black boxes and we use them, and sometimes they work a lot better than old-fashioned software that we try to understand. And so there comes this need to, for various reasons, to explain to a user, whoever that user may be, is it in a medical context, is it a doctor, is it the patient, is it an insurance company perhaps, who knows, why the algorithm came up with the answer that it did, why is this prediction what it is, what is the implication of this? And so we started thinking about it, and there were different aspects of this. My colleagues in sociology did interviews as well. This paper came out of, as we were thinking about explanations, we asked ourselves, well, in what other contexts do we see explanations structured in many ways in medicine? And the area that came up as we're talking was this area of informed consent. So if you go to have a procedure, your doctor is supposed to sit you down and walk you through what's going to happen and tell you about the risks in language that's understandable to you, and so that you can consent to the procedure that's done. It's part of personal autonomy, personal dignity, all of those things come into it. So when we looked at it, we thought, okay, well, here's an area that's similar but different, but it's been going on for a number of years, right? It's a well-established field. The AI explainability is a new field, right? People have been talking about it for the last few years, but nowhere near as much. So what can we learn from it? And so in the paper, I can walk through them. We ended up with sort of 5 lessons. You could argue should have been more or fewer, but the first was that clinical communications are provided to advance patient autonomy. So the very act of giving an explanation to the patient is important. It means you treat them with respect, with dignity. It's not just that they needed to make decisions, but just as a human being to a human being, they need that explanation. So the advice we came up with was, the explanations by themselves may be valuable, not just as a means to an end, and we need to specify purpose. The second, and I can walk through that, you can stop me, is that, you could provide many different ways. You can explain something in many different ways, but you have to do it in a way that benefits the patient. That's the lesson from the clinical realm. And so for us, the lesson was, don't try to explain everything, but perhaps different types of users in different targeted subsets, right? It's what are they going to do with this thing? And maybe that should drive how we think about explanation. In the clinical space, we have both rules and norms, and we need to think about professional norms about explainability. What should we think about? It shouldn't be just a compliance issue, but we should go beyond that. What we've learned in the clinical space for informed consent is that what constitutes a good clinical communications change over time. What was given 20, 30 years ago is not what's given now. And we need to think about also for our technical areas that what we think is a good explanation may not be in the future. We have to think about principles that we keep to, but the details will change. We have more sophisticated users. As people become more familiar with the technology, they will have different needs, different questions. And finally, communications are important for establishing trust in doctors and medicine. That's the lesson from clinical communications. And the same, we need to earn the trust of people as technology providers, not just for what they need or when they have questions, but we should explain what we do in general so that, it's not this scary technology thing, but maybe it helps them appreciate what it's doing. And we need to be open and transparent, and we need to talk about what we know and what we don't know. And, those are lessons that we also saw in action during the pandemic. And, I don't want to get into critiques and what went well and what didn't go well as we explained to the general public, but it's the same idea. We need to be transparent. We need to try to provide information and hopefully make people less scared of the technology and give them the ability to decide for what they need for their treatment purposes, right? And people have different needs. It's not the recommendation of an algorithm. It's just sort of, if we do this, this is likely to happen, but your ethical values, your personal values may say, no, I don't want that procedure. And that's what doctors have learned, and we need to think about that too. I don't know, maybe that's a very long-winded answer to a short question. I apologize.
Unlock the future of AI at Pitt HexAI. Pitt HexAI is where the brightest minds at the University of Pittsburgh come together to push the boundaries of artificial intelligence. Tune into the Pitt HexAI podcast to hear experts discuss cutting-edge AI research and its real-world impact. Join us at Pitt HexAI and listen to the podcast today.
No, I appreciate that. I especially like the second lesson to explain in a way that's useful. And along those lines, AI today is heavily used in medical imaging to help improve diagnostic accuracy, to improve workflow, to reduce workload. And there's really a broad spectrum of use cases that can range anywhere from things like automatic segmentation or lesion detection, quantitative analysis, automatic contouring, and image enhancement and reconstruction. So maybe a follow-up question would be, does the type of explainability that's needed, does it vary between the different use cases of AI? So for example, is simply having a clearly stated performance characteristic or set of characteristics adequate for some AI use cases where additional supporting clinical communication might be needed for others? Things like a nomogram for a risk prediction score or something along those lines.
Yeah, so I have come increasingly to think of the need for explanations, at least in a narrow sense, as almost a usability technique, right? So we've talked about human factors for a long time in medical devices, and how part of human factors usability engineering, really there are two goals, right, at a very high level. One is to make things easier for a user, make them happier to use a product, make it less stressful. Hopefully that makes it nicer to use, makes their life easier. So that's maybe the positive side of human factors of usability. And then the negative side of usability, of course, is to avoid errors, right? We need to design things in such a way that the user knows what's going on. And one of the things that comes out of that literature is that, you have to respect the user's sort of intuition here. So we don't have a green button that's marked stop, and we don't have a red button that marked go. So take that now, and let's think about AI in all of the cases that we talked about. Okay, so there's sort of one aspect of usability and explainability, which is, in my mind, those probably are synonymous here. A radiologist looked at the output of something and they need to provide a report. What information do we give them to make their life easier for them to describe what they have seen? So that's one level of explanation. And the other level, probably even more important in many cases, is how do we make sure that the reader has the information they need to say, well, is this algorithm correct? Is it wrong? How did it come up to an answer? How do I learn to trust it, right? Just a bit of background. Well, there's a ton of these AI tools in medicine. Almost all of them are human assist devices, which means that we rely on the human to be the risk manager, to spot the errors, which means we need to provide information for the human, the radiologist in this case, to identify errors. So for some cases, to go back to your example, automatic contouring, I say it's fairly easy. You need to show the result and you need to show it on the image, and the user can spot it. And yes, no, a reasonably competent human radiologist could tell you if your algorithm is wrong. Predictions about what will happen 5 years in the future, it's not as easy to sort of say, well, a user can't tell if you're right or wrong. You can try to tell a little bit of a story, try to say, well, these were the weighting factors that went into the decision, and now a user can learn to trust you or not. And honestly, ultimately, it's going to be experience. If over time these things prove to be correct, people will trust them more, but others will trust them less, and that's part of it. Reconstruction is one that scares me a little bit, because you don't even have the original image anymore to look at. Like, some of the AI has gone into creating the image. Has it changed the truth? But the reality is that we've always had algorithms doing this, and different choice of parameters could give you different images. So again, those are all part of the issue. So deep down, the question becomes, can we identify errors perhaps? And maybe also we may need to think about it in a little bit of a broader segment, right? So we do an imaging study, a radiologist reads it, and then that decision goes to another doctor who needs to recommend a treatment procedure, who may go to another doctor who needs to talk to a patient and say, well, these are your 3 options for how we do radiation treatment for your lung cancer, and this will give you more side effects of this kind, and this will improve the likelihood of treatment, and which one do you want to choose, because it's supposed to be a co-decision type situation. So sometimes we also need to think about explanations, not just for the immediate task, but how does it affect the entire pipeline? Like, some errors are not significant. Some errors could have dramatic impact on what the treatment decision goes down the road. And these are complicated problems, and often beyond what we can do, in product development, right? The average company just struggles enough to get performance characteristics for one user. So I don't know. That's a very long answer, but ultimately those are the challenges we have to deal with.
Well, I really appreciate 2 things that you mentioned there: the focus, the importance on usability and human factors, and having respect for the user's intuition. And it brings up one of the points I wanted to ask you about. In some of your work, you talk about the system as a concept, and it's broader than just the software or the AI algorithms that are being created. Can you explain what you mean by the system?
Yeah, it's unpublished work, but I've talked about it in enough different talks. So what is a system, right? So when we design a software system, a medical device system, a system is basically this box that does something, hopefully is more than the sum of its parts. That's the origin of systems theory, if you go back 100 years ago, give or take. And it's the thing that performs a task. One of the examples I use for my students is think about a system as like a walled city. The system goes inside the walls, the environment goes outside the walls, and the system and the environment communicate through maybe gates, which are the interfaces to the system. And so when we design a system to do a specific task, we identify where the walls are, we design the inside, and we guard our gates, we manage the interfaces. That's an arbitrary, abstract system theory, perhaps. Now, when it comes to thinking about AI in medicine, if you listen to people who do obsess about machine learning and just working, fundamental algorithm development, they think about, what is needed in radiology. Say it's a better neural network that will give you 3% better accuracy. But the reality is that that's not what the radiologist uses. What the radiologist uses is an image, is a software system that includes that algorithm, plus the display, plus how the information is presented, plus some explanations, plus the ability to highlight and measure and double check. So we need to think beyond just the AI and incorporate all these other things. The analogy I sometimes use for teaching is think of the AI as the engine of a car, but really users drive a car, right? The car is the system, the AI may be the engine, but users drive cars. And the joke sometimes is if you look out the window, you won't see naked engines down the street, you'll only see cars. So we have to think beyond the AI, and everything we talk about explainability is often, outside the AI. It may involve AI, it may not involve AI. What's good about explainability? Now, take that a step further. Given that the large majority of all AI used in medicine right now are meant as human assist devices, we need to think about the system even bigger. Like if I'm a patient, I'm getting a diagnosis, I get a diagnosis from this AI plus human system in some way. And so the human is part of the system in some crude way. There is a whole theory called system of systems theory, talks about, independent operations coming together to perform a task. So maybe that's a better analogy here. But so we need to evaluate, and that's literally what the FDA asks. The FDA asks you for the AI plus human result and the accuracy, not just purely the system. But that's just something to keep in mind. We are dealing with something not just an algorithm, not just a piece of software, but the entire, human plus AI. And again, if we have a healthcare pipeline, maybe multiple AI plus multiple humans that come together to generate a treatment plan or to execute a treatment. And it's good to think about this at this higher level, because ultimately we need to figure out how we do risk management in this space and across this more complicated system. And, the other part of the puzzle, and just to bring it back to education a little bit, if we think about the human now as part of some system, in the same way we try to improve the non-human components of the system to perform better, we need to think about how we improve the human. And ultimately, the one way that comes to mind is we need to train our humans to think about working with AI. It's not just the AI needs to be trained to generate outputs that are easy for a human to understand, but maybe we need to think about teaching the humans things to let them understand how AI works, right? It's like a driver's license. We design the car to be easy to drive, and then we teach the human how to drive. So to me, the educational part of what I do is also part of this development of these tools and thinking about how we train the users of the systems to be good users, to understand what's going on here. So maybe that sort of closes that loop.
It does. I really love the system approach. And I think it applies if you look at software as a medical device and the requirements to have a human in the loop. Things like clinical decision support software are not intended to replace the clinician, but ultimately to provide supporting information to help them if they're considering a potential diagnosis or maybe a treatment plan for a patient. So that makes a lot of sense. Maybe for students or practitioners, professionals who are aspiring in this particular field, what are some of the most important concepts they should understand when starting to work with AI in healthcare?
Yeah, I think the first one is what I had mentioned before, right? It's not just better machine learning tools. We have this, maybe this is how we are educated. We think about the better algorithm, right? The better segmentation algorithm. That's important, But there's a whole other complication set of systems, right? It's not the best algorithm that wins. Those of us old enough remember the arguments about Betamax and VHS. The same applies here. The algorithm needs to be put in a system. The system needs to be usable by human. It needs to be integrated into a healthcare workflow. It needs to have all those characteristics. And so my hope is that we figure out a way to train some next generation of people working in this space that understand the entire process. Because sometimes we spend a lot of time working on obsessing and optimizing a small part of the pipeline that may make no difference down the road, and we miss low-hanging fruits at the other end of the pipeline that may have more of an impact in, ultimately treating patients better and improving human health. So maybe that's what I would sort of emphasize. Like, I think, medical product development, and you know this better than I, you're in industry, I'm just working in a university here, it's a team process. You have a lot of people that come together. It's not like one person in the garage doing it. And I think it's important for the entire for everybody on the team, people to understand something about what everybody else on the team does and what constraints they are under. Because that may just make them do their part a little bit better in a way that helps the other members of the team, as opposed to in a way that sort of orthogonal to the needs of everybody else, and that includes the patient at the end of the day. So maybe that's kind of, if I have any advice, that's what I would offer here.
I think that's great. The emphasis, the importance of working across cross-functional teams, so important within medical technology, healthcare technology, spot on for sure. Maybe one more question for researchers and students that might be listening to our podcast. We typically like to include this. Are there any specific areas or research projects that you think might be interesting or relevant for students that are focused on the intersection of AI and potentially medical devices, software used in healthcare? Is there anything that you think is of interest that might be a good area you would recommend?
That's a tough question. Obviously, even now, we've made huge advancements in AI machine learning, but better AI machine learning, I said that nobody drives engines that drive cars, but better engines are always good. So that's useful area to work. But ultimately, then this is just my personal bias. This is what I've worked on or I've ended up working on over the years. I think a lot of science is done, and to pick up on your interdisciplinary aspect, it's done in silos, right? The software engineers want to write better code. The AI people want to do better neural network. The regulatory people want to do a better job of, answering the questions they have to answer. The testers want to do better testing. And all of those things are good and individually are fine. I think the biggest improvements are going to come when we train people who can work across those boundaries and be the sort of person who knows how to bridge software engineering to machine learning, or testing to regulatory, or whatever the pairs that come adjacent to each other, because that's where we lose things. When I teach this class, often the example I give to students early on, and maybe this is your last picture here, is I said this pro is often like a game of telephone, right? The game that many people play as children. You have children, they sit in line, and the first child whispers something to the ear of the next child, and on and on and on. And what the last child hears is nothing to do with what the first child said. And often complicated process like designing a complicated system, building it, implementing it all the way is that game of telephone. There's different specialties and they all transmit some information and something is lost along the way. And hopefully what comes out at the end at least is somewhat related to what we wanted when we started. And so having people who can process information across these disciplines and thinking about what it takes to do that, what is, explainability in AI is a good example, bridging the output of an algorithm to what a human needs. And you can think of others that way. I think those are going to be important skills, because the specialist skills, I think we know how to do to a large extent, but that interfacing type skill, those interfacing type projects are harder to do. The one project I described before that we talked about, the research on clinical communications, and the other project, the biggest challenge of that project, we all had to learn to talk to each other because we all came from our own backgrounds. And my sociology colleague and my software engineering colleague, did not have a shared language when we started. By now they can talk and we all managed to figure out a common language. But I think that, to me, is the most exciting thing to do about it. It's harder because specialist research is easier to evaluate, easier to get accepted. But I think this sort of interface type work, to me at least, is ultimately more valuable. We'll see. I've been wrong before and I'll be wrong again. So,
well, I think I really appreciate the perspective that you've brought and thinking about it in the context of there's different individuals focusing on different areas that have different understanding, and the collaboration you've done to, just like on the publication of working with somebody with a sociology background, medical background, software engineering, it's really important to be able to address the needs of different end users. So that's great insight, and we really appreciate you spending some time with us today, Dr. Papademetris. It's been great having you as our guest on the Pitt HexAI podcast. So thanks to all our listeners that tuned in today. This concludes our podcast episode. We hope you enjoyed the discussion with Dr. Xenophon Papademetris, Professor of Biomedical Informatics and Data Science and Radiology and Biomedical Imaging at Yale School of Medicine. Thank you for listening.
Thanks everyone for tuning in and for following the show. The Health and Explainable AI podcast is produced by the University of Pittsburgh's Health and Explainable AI Research Laboratory at University of Pittsburgh School of Health and Rehabilitation Sciences Department of Health Information Management. I'm Jordan Gaspore. Thanks for listening.